Hey AP Physics, here's a little bit of notes in video form for you. You need to watch these notes before this is a fantastic pen. Before you try problems number, let's see, 49, 51, 53, 60, and 61. But I think I went back and I looked at these problems a little bit earlier, and if I am remembering correctly, it's really only for 61 that you need absolutely what I'm going to show you here. But I just want to talk about, in general, what are the concerns or what's up with energy in collisions. And I'll put collisions in quotation marks, because that could also mean what we would call an explosion, where two things are stuck together and then there's some release. Could be a spring or some kind of detonation of some kind that forces the two objects apart. So, in general, if energy is lost, we call that an inelastic collision. If energy is conserved, we call that an elastic collision. And maybe worth mentioning that this condition, an elastic collision, this is an ideal kind of situation, similar maybe to a frictionless surface or something like that, where we assume that there's no friction. That doesn't actually happen ever. So this conservation of energy, this elastic collision, is an ideal. And we don't usually see that. But some collisions are very, very close to that, so we would assume that they are, in fact, and we would call them elastic. So that's that. And if energy is gained, well, that can only happen if there was some other something storing energy before the quote-unquote collision, and we'll really call that an explosion. So if there was a spring that was all compressed that forced the two objects apart, then we're going to have a gain in energy. And in all of these, linear momentum is conserved. In all three cases. Well, that's always true. Okay, so that's it, really. I think I'm just going to do one example for you of an elastic collision, so you can see how that plays out. So let's do that. You saw in class the carts with the magnetic ends that bounce off each other without actually touching. That's pretty much as close as we can come in our lab with our equipment to an elastic collision, where two things bounce off each other. If two things stick together, that is an inelastic collision by just by observation. Two things sticking together, most definitely an inelastic collision. There's a big, you could think of these, the perfect inelastic collision where two objects stick together as one end of a spectrum, and the elastic collision being at the other end. And the vast majority of actual collisions that happen in the so-called real world are somewhere on that spectrum. Now, momentum was always going to be conserved. This is not compromised, but only at this end of the spectrum where you have an elastic collision is energy, kinetic energy, conserved. And I guess I implied here that when we say if energy is lost, energy conserved, energy gained, this is kinetic energy. That's what we're talking about here. I implied that, but I should state that very clearly here. That's what we're talking about. Okay, so what about when we have two carts, and in the before situation we have a cart, let's say it has a mass m, and it's traveling in this direction, as you can see by the little zoomy lines behind it, and let's say that it has a velocity of how about 3 meters per second, and it collides with another cart. Let's say this has a mass of 2m, and let's say that that initially has a velocity of 0. And then after the collision, well, we don't know what happens. There's still two carts. Conservation of number of carts. But we don't know what's going on with them after the collision. You might remember, and maybe it seems intuitively correct to you, that this cart, with the crashing into one that's more massive, it's actually going to bounce backward, and it will have some velocity in this direction, and this one will have some velocity in this direction. And momentum will be conserved, and if it's an elastic collision, which means the change in kinetic energy is 0. Now, I'll just state here also that the key thing that I want you to understand here is that sometimes when you see problems like this, it will be stated that the collision is elastic, and you need to understand that that means that kinetic energy is also conserved. In other words, the problem will typically not state kinetic energy is conserved. The problem will state that the collision is elastic, and you need to know that that means kinetic energy is conserved. All right, so momentum is conserved. So let's write a equation for that. So that means the total momentum before and the total momentum after are the same. So what does that equation look like? Well, before I have this cart with a mass of 3 times its velocity. I'm going to drop the units here just for ease of calculation. You can assume that all the correct units are there. And then the second cart has a mass of 2m, but its velocity is 0. So the total momentum of the system is just this 3m. And then on the other side, I have this cart of mass m, and I'm going to call that v1. It's unambiguous, I think, that I mean the velocities after, because I know the ones before. So that has velocity v1. I don't know what it is. And then here I have this cart of mass 2m, and then there's its final velocity. We call that v2. And you can see here that the problem is I can cancel out an m from everywhere, but I end up with an equation that says 3 is equal to v1 plus 2 v2. So we've got a relationship between v1 and v2, but just knowing that momentum is conserved is not enough to solve for either, never mind, both of the velocities. So since it's elastic, I know that kinetic, the T comes before the C in that word, kinetic energy is conserved. So let's see, that means the sum of the kinetic energies before is equal to the sum of the kinetic energies after. So I'll set up an equation just like this. So I've got 1/2 mv squared plus, I'm writing this in, if you know what's going on here, you could probably just leave that term out because you know it's going to go away. There's ain't no velocity there. And then we got 1/2 mv1 squared plus 1/2 mv2 squared. And maybe you kind of see where this is going, that we're going to end up with a system of equations. So the m is going to cancel out from all the terms, and the 1/2 is also going to cancel out from all the terms. So let's see what we have after we cancel out the 1/2 m. So here I have 9 on this side. Again, I'm dropping the units now, all the correct units. That would be 9 meters squared per second squared. 1/2 m cancels out, so that's v1 squared. 1/2 m cancels out. The 2 does not cancel out. And I just need to solve this system now. So how would you like to do that? Well, we could take this equation here, say, well, v1 then is going to be equal to 3 minus 2 v2, and then substitute here. Get a little bit more room there. So 9 is equal to this expression that I'm going to substitute here, u2 squared plus 2 squared, like that. And let's see, we have here, so that's going to be 9 minus 6, so is 12 v2, right, plus 4 v2 squared plus 2 v2 squared. And the 9's cancel out, and rearranging things a little bit, combining some of the old like terms. 6 v2 squared minus 12 v2, and in this particular case the numbers were nice, so I can solve this easily without a calculator. It's possible you could end up with a messier situation. You might need to do a little calculator work. So it looks like the velocity of cart 2 is 2 meters per second. And that means the velocity of cart 1 is equal to, we can go either way. This is kind of set up to give us v1 here. So it'd be 3 minus 2 times v2, so that's negative 1 meters per second, which confirms our intuition that that one would be going the other way. So there are those velocities. If you wanted to, you could check to see that the kinetic energy is conserved. You could just check both sides. If we did all our algebra right, of course these equations have to be true. So here's my initial kinetic energy. So 1/2 m times 3 squared, that'd be 9/2 m. And then on this side, I'd have 1/2 m times 1 negative 1 squared 1, so that'd be 1/2 an m. And here, the 1/2 and the 2 cancel out, that's an m, so 4 plus 1/2, that's 4.5, or 9/2. So that checks out. And you could also check them to see that the momentum is conserved. So my momentum beforehand is 3m, and then here I'd have negative 1m and positive 4m, that's 3m, so it's all good. So notice here that the problem with these elastic collisions where the objects bounce off each other is that there are too many. If we only knew that momentum was conserved, then we just wouldn't have enough information to figure out what was happening. Too many variables because of the two different velocities after the collision. If the two objects stick together, this is not a problem for us because the velocity of both objects, you could treat them just like one object. In this case, it would be an object of 3m. So in this case, it's extremely helpful and almost like the physics of everything new that we would need to have another relationship here. And that relationship is kinetic energy is conserved. And that gives us enough information to solve that by a system of equations. There you go. Have fun. Hope you enjoy your snow day. And I'll try to get this uploaded. And I'll put in the title, I guess you know this by now because you would have found it, but I'll put in the title that what this video is and when you should watch it. Bye.